This is the video for 6-5 day 1. Simpson's rule is going to be the title for this, but first work on your warm-ups. Answer each of the three below. They're not looking for a numerical answer, they're looking for what it represents in words, and then come back to the video. If you're back, that's because you have your warm-ups done. And now you're ready to compare. So f of 6, because this is the rate graph, f of 6 then is the velocity at exactly time 6 seconds, or the rate of change, or the speed of the cyclist at time 6 seconds in a forward direction. 2 then would be the displacement. Since they are all positive values of the velocity, it is fair to say that the sum of the distances traveled would be okay here. Normally you'd need an absolute value here, but all the values of the velocity are positive, or you could say because they're all positive that this is the total distance traveled in the first 6 seconds. Number 3 would be the acceleration, or the rate of change of speed at time 6 seconds, the rate of change of speed in the positive direction at time 6 seconds. Simpson's rule that we're going to work on for a few days is another way to evaluate integrals that are definite integrals, a space under the curve between two values on the x-axis. So as we've done definite integrals from chapter 6, the first thing you learned to do them by was by area. So as we look at the methods you already have, you have 3. And the first method you had to or have to evaluate definite integrals is to find an antiderivative. If we'd given you the function, you could evaluate the antiderivative over the interval 0 to 6. You do know that your calculator can do some math to get a nice approximation for a definite integral. And finally, you know that you have methods by which we found them numerically at first by finding areas. So the 4 methods that we had were first by finding areas of rectangles that fit under the curve in different ways. So left rectangular approximation, right rectangular, midpoint rectangular approximation, and then a better fit was trapezoid approximation. Simpson's rule is going to add one more shape to this. So as we look through what we knew about left rectangular approximation, depending on what the curve looked like, that could be an over or under estimate. So for our particular curve, if we wanted to break this into, let's say, 3 rectangles, our first rectangle's height starts at the left with left rectangular, so our first rectangle would contribute 0 to the total area under the curve for that interval. For the next interval, its height would start at the left, and we would be underestimating that region, as we clearly underestimated the first region. And for this curve, we're underestimating when we put in that last left rectangle. So for this curve, it's underestimating. That's not true for all curves. For some curves, it overestimates. Then as we go through and we put in the right rectangular on this particular curve for the same intervals, our right rectangular is going to have us overestimating because those rectangles from the right-hand side are above the curve, and so we're including some area in that estimate that we would not normally include. So for this particular graph, right rectangular overestimates or over approximates the area. It's a little hard to tell what the midpoint one is doing. Not all midpoints are exactly the same depending on the shape of your curve, meaning sometimes they over approximate, sometimes they under approximate. This one tends to do better than left or right, but it's a little hard to tell if it's going to over approximate or under approximate in this case because it's including some area it shouldn't, but it's also leaving out some area that it should count. So in this case, a little hard to tell. So then we moved on to trapezoidal, and we said trapezoidal is almost always a better fit. Okay? Even if the graph is rectangular in shape, it would be the exact same. So 2 reasons that we prefer trapezoidal: it's a better fit than rectangles for most curves, and it's equal to the average of the left and the right rectangular approximation values. You can find it that way as well. So it evens out some of that under and over estimation that trapezoids do. What we also knew about trapezoidal was if it's concave down, as our graph is at the moment, then when we put in our trapezoidal shapes, our trapezoid sides that we're putting in are going to be under the curve, and therefore if it's concave down, it always underestimates or under approximates the value of the integral. And ours is a concave down curve at the moment. Our second derivative would be negative for this curve. So we do know that this curve itself is concave down, so our trapezoids would under approximate. If our curve is concave up, then our trapezoid side lengths are going to be over the curve, and therefore our trapezoids are going to include a little extra area, and it always over approximates if the curve itself is concave up. When we add this new method in, we're going to try to get rid of some of that error that comes from all the methods that we've got. So the amount of error in trapezoid rule depends on two things. It depends on how curvy f of x is. The less curvy, the better trapezoids would fit, like that first example. Those last three trapezoids fit really well because the curve is not nearly as curvy. It's not a technical math word. In the second one, though, you can see that none of those trapezoids fit quite as well. So the other thing that it depends on, because we could make those intervals shorter and try to fit the curves better, so it also depends on how large the subintervals are. The larger we make them, the harder it is for those trapezoids to fit a curve. So Simpson's method does away with all that because Simpson's method is going to fit a parabola to each of the intervals that you break your axis into. So it gets away from worrying about how curvy it really is. And it says we can fit parabolas to anything. So Simpson's rule, instead of fitting rectangles or trapezoids, is going to fit a parabola to each subregion. And there's a rule, and it's demonstrated right there with S equals, and the S stands for the approximation based on Simpson's rule of fitting parabolas to each subinterval. So it can fit a curve to that subinterval and work on getting the area under that curve to add in for the integral value. And then it goes to the next interval and fits a trapezoidal curve under that. So a few things to know about using this rule, and then we'll dig in and just start to use it right away. N is the number of subintervals that you break things into. And since it's the number of subintervals that we break things into, the thing we need to know is that that needs to be even for Simpson's rule. It didn't need to be even for any of the other ones, but it needs to be an even number. The reason is it's kind of fitting the parabolas to two regions at a time. So this must be an even number because it needs 3 data points to fit a curve. Okay, so what h is then is h is the length of each of your subintervals. And how you calculate that is exactly how we've calculated it before. Your highest x value that you're going from, in this case our b would be 6 to our lowest x value that we're going for, so this would be 6 minus 0 divided by however many subregions we were making. In Simpson's rule, they also need to be equal subintervals in order to use the rule. Just like trapezoid rule, to use the shortcut formula, you need them to be equal in size. So the amount of error for Simpson's rule then using parabolas doesn't depend on the shape of the graph. So the shape of the graph can have curves, and we can fit curves to curves much better than we can fit straight things. So the amount of error that Simpson's rule comes up with between it and the exact value of the integral depends only on the size of the subintervals, or how many that you use. It does not depend on the shape of the graph at all. So whether the graph's concave up or concave down, whether it's more curvy or less curvy, we can fit trapezoids to parabolas to anything better than we can fit trapezoids to most things. So we're going to try this out. We're going to give an example. We're going to try it by trapezoid rule first, see what we get. Then we'll go back and we'll try it by Simpson's rule and see what we get. And then we'll make a comparison to the exact. So the formula, the integral that we're looking for is the integral from 0 to 6 of the function square root of 2x. We're just going to start, because we're doing this by hand, with only 4 subintervals. So knowing that we're splitting this into 4 subintervals, our n is 4. So then as we go to calculate the things that we need the length of each equal subinterval. And since we're going from 6 to 0, 6 minus 0, that's the b minus a, divided by 4 subintervals. Each subinterval is going to be 3/2 of a unit long, so we're looking at going from 0 to 1.5. From 3/2 up to 3, from 3 up to 4.5 or 9/2, and then from 9/2 up to 6, so that we have 4 equal subintervals. When we did this with trapezoids, it helped many of you to actually write out that along the x-axis, what your in-between x values were going to be. So we'll start by approximating with trapezoid rule. Trapezoid rule, or individual trapezoids if you've forgotten the shortcut rule, which is fine, Trapezoid rule pulled the half out front that all trapezoids have in their formula, and then it pulled out the 3/2, which is the height of each trapezoid if we were to put trapezoids in. And the shortcut way to do it then was to start with the first y output for your beginning value interval, which is 0 to 3/2, and y at 0, and plugging that back into the formula. So we're going for our y values from right there. So y at 0 is 0. That would be the first height of the first trapezoid we would be making, or base length, I should say. And then because the next height on our graph is going to get used as the base of two different trapezoids, we need twice the y value at 3/2 and twice the y value at 3/2. It's going to be 2 square roots of 3. Pause the video, fill the rest of these in so that you can see that you can get these and know where they come from, and then come back and see what you got. Remember, all the ones in between the first and the last value get used twice in the formula because they are the bases of two different trapezoids as you're going through and doing your work. Okay, the first and the last one only get used once. So if you go calculate that out, the estimation for the value of that integral is about 13.370. For the area under the curve between the curve and the x-axis from 0 to 6 by trapezoids. And you can see because it's curvy, here's what I know. I know because this whole thing is concave down at the moment that this is an under approximation. So if I had more subregions, I'd get a better trapezoidal approximation, but I'm still going to be under approximating or underestimating with the trapezoid rule because it's a concave down curve. Simpson's rule takes that away. Simpson's rule says, okay, to calculate this, and this comes from the formula, the third is part of the formula. This is the length of each sub-interval. And then Simpson's rule has a different pattern. It takes the first y value from the beginning of your interval, then it goes back and forth between 4 times the value of your y's and 2 times the value of your y's until we get to the very last one. So in some ways it's like trapezoid rule. The first and the last y value are kept, but in between it toggles back and forth between 4 times the quantity at that particular location and only 2 times. And it's kind of evening out that trapezoid rule underestimation at the moment because this is going to put a little more into it. So pause the video, go back and fill yours in, see that you can get the same thing so you know where these come from. And then if you calculate this one, we're around 13 points, and I just 646. And that's not a lot of subintervals for either one of them. We only did 4 because we were doing it by hand. So to get the exact value, let's actually go ahead and do the calculus to get the exact value of the integral to see how close we got. And then I'll show you if you put in more subintervals. And doing that by hand is a little tedious, and that's why we didn't. But if you put in more subintervals, how much closer we would be with Simpson's rule than with even trapezoidal rule. So doing the calculus here, I'd want to integrate, okay? And doing that, I could do a little substitution here, a little u substitution over on the side so that I could carry this out. So I might make my u2x. I would really like to have an extra 2 in here in order to carry out the integration, so I'll need a half out front. When I switch to u's and I actually substitute, so please don't skip steps, when I actually substitute and switch my integral over to u's, and this will become u to the 1/2 du, I want to switch my bounds over as well. I'm not doing 0 to 6 anymore because I'm not using x's. So now that I'm using u's, twice u, the value of 0 is 0, twice an x value of 6 is 12, so in u terms I'm doing 0 to 12. So when I actually integrate, I've got 1/2, then I'm going to have 2/3 u to the 3/2 as my antiderivative, evaluated from 0 to 12. I'm going to clean that up just the littlest bit so that I don't need to do as much, so that's really 1/3 the value of u to the 3/2 power. So I have 1/3. Value of u to the 3/2 power, so I need 12 to the 3/2 power minus 0 to the 3/2 power. 12 to the 3/2 power ends up being a value we can calculate with our calculator. It's not a nice whole number. And the exact value for this integral, or much closer, because we did it from the calculus, it is rounded off a little bit, is in the 13.8 neighborhood. Now just to show you, I did a little bit of work with more subregions, and more subregions gets our Simpson's rule value much closer to this. Remember, Simpson's rule does not depend on the shape. Our trapezoid rule is always going to underestimate this because it's concave down, whereas our Simpson's rule is going to get a lot closer. 6 subregions, and our Simpson's rule is at 13.7-ish. 12 subregions, and we're already within 4/100ths of the value of that integral exactly. So you're going to use this in your assignment tonight. You're going to use trapezoidal rule at first, and then you're going to use Simpson's rule. Please check the syllabus for which parts of each problem you need to do. Please make sure that you're showing calculus to demonstrate your concavity. So it's not, well, I looked at the graph and I know it's concave up or concave down. Please use second derivative and use calculus to demonstrate your concavity. And let me know if you have questions.